All right, so yesterday we finished the lesson with this investigation. If you remember, we had a transformation matrix. We applied it to, I think we chose 5 points on this line, and we realized that they were still on the line, but they had been stretched out. And then we did it with like this general point, and we saw that they were 3 times further out. And then we also did it with points on the line y equals x, and we found that for the line y equals x, it was 2 times further out. Now, if we had the time and energy, we could have explored other lines. And what we would have found with other lines is that it wouldn't have worked in the same way. They would not have been stretched back onto the same line. In fact, the only 2 lines that this works for this matrix are y equals 2x and y equals x. Okay? So what is happening with this is we're taking points. I'm going to draw some axes. We've got x and y and the origin. We had y equals 2x, so it's kind of like that, and we had y equals x. And what's happening is if we have a point on y equals 2x, it's stretched 3 times out from the origin. That's roughly 3 times out. And it moves to a new position. If we had a point here, it's 1, 2, there-ish. It's moved 3 times further out. And the blue one is y equals x. It was being doubled. Okay, so that's giving us some indication of how that matrix is transforming things. It only works for these 2 lines though. All other points off those lines are going to be stretched in different ways according to these 2 stretch factors. Okay, so we're going to move on to the next page, and we'll talk about these lines and these stretch factors. We're going to introduce some terminology, and we're going to look at how we can find them, because you were told the lines in this instance, and so you just confirmed that it was happening. But we want to be able to find these lines, because this is telling us something about the matrix that we're dealing with. Okay, so the above investigation shows that in general a matrix has 2 lines associated with it, and any points on these lines stay on the lines when multiplied by the matrix, though they may be moved to a different point on the line. The line is invariant, but the points are not. That means this line does not change. We do not go off the line, but we just slide along the line. Okay? And it will, for this matrix, it will always be these 2 lines. Yeah?
So can we do it like normally where we have like several points, and then we can say if the new point is on the line, we can find the slope?
We could. The trouble is, you've got like infinite oh, I see. Like if you took some points and saw where they moved to,
yes.
Could we try and deduce what the line is?
Yeah, with the slope.
The trouble is, it would have to be a point on the line. Like if I chose this point here, this isn't on the blue line or the purple line.
But I thought we were finding points on the line that move on the line. Because
how do you know where the line is though?
That's what I'm saying. We could find out the line by finding out the slope, by finding out where the point moves to.
But if I chose this point, it wouldn't be on the line. I think we've got an issue here where if I choose a point on the line, it will tell me that it's on the line.
Yeah.
But if I don't choose a point on the line, it's not on the line, and it won't tell me where the line is. It's a good idea. But yeah, I think unless we got lucky and chose a point on the line, it's not going to show us anything. And there's so many lines that the chance of choosing a point that's on a line is pretty slim. Yeah, Ethan.
Can you multiply the vector or the matrix by xy, like a xy?
Like just a general point?
Yeah. And then you get like, I did it here, I got 1x plus 4y. No. I'll think of it.
I don't think there's going to be enough information from it. No. But we will look at a way of finding these lines. So a vector in the direction of each invariant line is called an eigenvector of the matrix. So what would be a vector in the direction of this purple line? Give me a vector that passes along that purple line or moves in the same direction. Oh.
8, 4.
8, 4. 8 to the right and 4 up?
No, the other way.
4, 8. Yep, 4, 8 would be a vector that moves in the direction of that line. Give me a different vector that moves in the direction of that line.
2, 0.
2, 0.
Oh wait, 0, 2.
0, 2 would
Oh,
take me to there.
2, 0. Wait, no.
2, 0, take me to there.
Ah. Wait, 2, 4.
2, 4 would work. Yeah. Ethan, did you have a different one?
1, 2.
1, 2. Yep. All of them are expressing that same vector, that same direction. Can I have a vector that moves in the direction of the blue line? Someone else?
2, 2.
2, 2. Yep.
4, 4.
4, 4. Or even 1, 1. Okay. So let's go back to this page. Okay, a vector in the direction of each invariant line is called an eigenvector of the matrix. So we have found an eigenvector of the matrix. Any of these would be one eigenvector, and any of the purple ones would be another eigenvector. The stretch factor is the associated eigenvalue. So the stretch factor for the purple line was 3. So the eigenvector describing this is 1, 2. The stretch factor is 3, and the notation we typically use is lambda for that. And then for the other one, I think it was a stretch factor of 2. Memory of our last lesson.
Yeah.
Yeah.
Wait, if you go back.
Yeah.
Can it be that there's a pattern that with the scale factor, stretch factor thingy? Because if it's y equals x, it's 2, and if it's y equals 2 x, it's
Coincidence, I'm afraid.
No.
Yeah. Nice to look for these patterns, but I'm afraid that is coincidence. Okay, these are very important values when considering a dynamic system. So today we're going to look at finding the eigenvalues and eigenvectors for a matrix. I'm just going to pause. Well, actually, I'm going to stop.